It's it's my pleasure to invite Dr. Miltos Alamaniotis, who is an assistant professor in the Department of Electrical and Computer Engineering at UTSA. Before joining UTSA, he worked as a researcher at Purdue University, and he received his bachelor's in electrical and computer engineering from University of Thessaly in 2005 and an MS and PhD in nuclear engineering with an emphasis in applied AI from Purdue University. His research really is very interdisciplinary in nature, where he focuses on the development of intelligent systems and machine learning approaches applied to energy systems, electric power grids, nuclear power systems, and nuclear security to detect hidden radioactive materials. He has extensively published over 200 articles, and his research is recognized in UTSA with the Distinguished Research Achievements at UTSA in April 2002. And he's also the recipient of Distinguished Alumnus Award from his Department of ECE at University of Thessaly. And he has experience working in several national labs. And Dr. Miltos's research is something that where you can see AI helping in our national security. And it's a very important conversation to have for Matrix and for some of our students. So thank you so much for joining us today, Miltos, to share your research on how you're using AI to help in improving the security of the nation.
Thank you, Teresa. Actually, it's my honor to be invited here. Okay, though it happened in the last 2 days, but it's a really honor to present to the Matrix the work that I'm doing here at the UTSA. So actually, today's talk it is entitled "The Deterrence of a Nuclear September 11th: Solutions of Artificial Intelligence in Enhancing Nuclear Security of Urban Areas." And it has to do, actually, as you may see from the title, on how we can improve actually national security, and actually emphasizing on improvement against nuclear threats. So today I'm going to talk about the fear of a new type of 9/11, actually what we call a nuclear 9/11, and how nuclear security, what's actually the goal of nuclear security, and how artificial intelligence can be applied to enhance, the solutions that are needed in the nuclear security enterprise. Also, the use of AI, it might be positive, but also it might raise some concerns and some, responsibilities, because we are talking about a very critical area. So I'm going to give an overview of what are these concerns and how we may, what we need to think and how we may overcome them. And at the end, I'm going to give a summary of the talk. So before getting into the technical details, I need to say that actually what happened in Twin Towers in New York almost 22 years ago made actually the whole security architecture to be revisited. Okay, there were two skyscrapers there, that were destroyed, but then after that, revisiting the security came to our mind that okay, something more severe that may happen, and this severe thing actually has been recognized as being new threats, and new threats in the form of nuclear, because nuclear weapons, nuclear material can provide can provide much higher number of deaths, if detonation of nuclear, let's say, weapon device actually happens. So having these nuclear threats being identified as one of the major things that our urban areas are in a risk, this nuclear terrorism actually is expressed in the following three ways. Okay, either they use, actually the simplest is the one that comes to our minds is the use of nuclear weapons. Okay, everybody knows that, because everybody has in mind what happened, in Hiroshima in Japan, actually almost a decade back. But also the new types of nuclear terrorism that can be seen actually in urban areas is that detonation of small-scale explosion devices, especially those that they have nuclear material, either nuclear material that is being used as a weapon or nuclear material that is upon an explosive device, what we call a dirty bomb. And this may result in dispersion of nuclear material in the environment. So the problem that was identified here is that this new form of terrorism is not, let's say, a terrorism that happens within 2 or 3 minutes and that's all. If detonation of nuclear material, dispersion of nuclear material happens, this will stay there for a long time. So it's gonna be, let's say, a terroristic event that is gonna last for a long time. Okay, and having that in mind, the consequences of a nuclear 9/11 definitely are gonna be more severe. Okay, because the material, as I said, is gonna stay there for a long time. So we are going to have a higher number of deaths, and these deaths, they're not going to be only directly, they're not going to be direct deaths that at the time of the explosion, but they're going to happen after some time, because people will be exposed to radiation and this, let's say, hazardous environment. Okay, and definitely urban areas will become inhabitant, will have to become inhabitant for some period. Okay, because you cannot live in a radioactive environment. So this is something that we call a nuclear 9/11, and it's really something we really want to avoid, to deter. Okay, so now what about nuclear security and what's its architecture? Okay, nuclear security, the definition, there's no specific definition, but pretty much what it has to do is that contains all those activities that have to do with nuclear materials. Okay, and the main goal of nuclear security is how to secure that, let's say, in simple words, we need to know whenever there is a nuclear material, wherever there is or wherever it goes, we need to know, we need to have this information. So there are two parts actually in nuclear security. The first one that has to do with that deals with the declared and counted nuclear material. So we know everything. We know the material, where it is stored, where it is moved. Okay, and also there is a branch of nuclear security that has to do with the undeclared, the illicit material, the one that is is hidden somewhere, or it is being moved without any authorization. Okay, and this actually is the part that has to do with the terroristic attacks. Okay, because if someone wants to perform, to conduct actually a terroristic attack in an urban area, definitely will use material that is undeclared or it is being stolen, and he hides it somewhere. Okay, so one of the things that nuclear security architecture has identified is that one of the first line of defenses that we do have is that we need to identify the use, storage, and move of these nuclear materials. Or in other words, can we detect the material before it gets detonated, dispersed? And in that actually area, there are some challenges that have to be actually there are some challenges that we have to overcome. Okay, to have a fully and let's say a fully functioning nuclear security domain, we need those challenges to overcome. And specific challenges are the following. For example, identify the origins of nuclear materials, where they come from. Okay, how they have been used. Second, we need to monitor the global fissile material production. Okay, that means, in other words, where are the nuclear power plants? Okay, what's happening with the spent fuel? Where does it go? Do we store it in a safe place? Then we need something that happened actually the last 30 years. We need to monitor the Russian nuclear warhead dismantling after the collapse of Soviet Union. Soviet Union actually was full of nuclear warheads. Okay, it had even more than United States, and with the collapse, these actually warheads were actually in great dangers to be, to be stolen or to be taken by wrong people and sell them in, for example, in the black market. So we have to see how they get dismantled. Okay, very important thing for nuclear security challenges: counter nuclear smuggling and enhance international safeguards. And this actually has to do with the borders. Okay, we're in Texas, for example, and we need to secure that the south border of the United States is secure and nobody tries to smuggle in nuclear material, from other countries. Okay, from countries that material that has been sold and actually bought actually in a black market, and you have to smuggle it through the border. So we need not only to check, for example, in the borders how many people get in, and but also we need to check whether these people, or the cars, they have nuclear material hidden in them. Okay, and you see here the picture that I do have. This is actually from the border, if I recall well, from Arizona. And you see that one of the challenges here is that, can you check very fast and very efficient all those cars that indeed they don't have a small amount of nuclear material with them? That's a real challenge, from computationally, and from physics and computational point of view. Now, one very important part of nuclear security is the detection. Okay, detection systems, actually what we call in electrical engineering, computer engineering, I would say, data acquisition. Okay, so I provide here the architecture of a detection system, and for electrical engineering students, this should be very familiar, how it detects, how the system works. Although this is something that most nuclear engineering students, are being, let's say, taught. They're taught this material, and they're being used in their labs. So let's say we have a source, we have the hardware element, which is actually the sensor or the detector. Okay, one of the one of the widest used detectors is the Geiger-Müller. I'm pretty sure everybody has heard that before. Then the detector has the preamplifier. The preamplifier gets the signal, amplifies it, and then sends it to the amplifier, where there is let's say the actual amplification of the signal. And then based on the detection system, it goes to the multi-channel analyzer, where it provides, actually the multi-channel analyzer, it's like a classification system that classifies the types of radiation into energy beams. Okay, so you can see it as what we call in nuclear multi-channel is actually a histogram in statistics, as we say in engineering, a histogram of a signal, I would say. Okay, and then the signal that is being developed in the multi-channel analyzer is being, fed to the computer, where there is the signal analysis and decision-making system. It's actually where the AI software can reside and analyze the data that we get. Now, signals that we obtain actually in nuclear security, and we have to analyze, are the ones that you see here in your monitor. Okay, those signals, they have different challenges, different analysis challenges. Okay, for example, the first one is a signal that we get with a mobile low resolution detector. Okay, it is being acquired during a source search. That means we have a mobile detector, and we go around to find whether there is or where is a hidden source. And the big challenge is that you see that there is that the signal has a high variation. Okay, you see that it shows some spectral peaks that they come out of noise. They come out of what we call background radiation, and sometimes these signals, this actually variation in signal, hides the features of the signal that are related to nuclear material. Okay, and the problem with mobile detectors is that They move all the time, so it's really difficult to, let's say, acquire a signal that is a representative of the location, because if something moves, changes, locations all the time. Okay, so you have to do a trade-off of how much time you're going to spend in a specific location and how much time you're going to get your signal. Okay, usually the thing is that the higher that you stay in a location, the better, the smoother your signal becomes, and this is what we need. But we don't have this opportunity in nuclear security, because you need to survey a big area. So one of the problems here is this one, the trade-off between location and acquisition time, that actually leads to high variation. Another signal here is the gamma ray spectrum. Okay, you see that again, although it has been this gamma ray spectrum it has been acquired with a static, what we call sodium iodine detector, which is also of low resolution. And again, you see the signal is very smoother than the previous one, but the problem here is that in the first 200 energy channels, what we call in nuclear the low energy area, it shows an elevated number of counts. Okay, and that means it comes from background radiation, and any nuclear material that has patterns that can be identified in this area is hidden. Now, another type of signal is the nuclear resonance fluorescence spectrum. Okay, this has very nice features. The spectral peaks are very nicely seen, actually observed in this signal. But the problem with this signal is that it requires specific devices, and actually it's very costly to obtain it, because it's not passive, it's active. You have to energize a material to emit this radiation so you can acquire it. The biggest, actually, from a data analysis point of view, the challenge that we do have in this type of signals is that every measurement here, for example, those three data sets you see here, the spectra, as we call them in nuclear, they are aggregation of patterns. Okay, they don't come from a single isotope, but they are coming from multiple isotopes. So they get aggregated, actually they get convolved, and that's a difficult. How can you deconvolve those signals and identify the patterns hidden in them? One of the problems that we do have is that the measurement we get, actually the pattern we observe, might come from a source pattern of interest, but might also come from, and actually in 99% of the cases, come from what we call the background pattern, because a background pattern is the radiation that is a natural radiation that actually it's everywhere. Okay, now if you are at your home, the construction materials of your apartment or your house emit some radiation, but this is natural, so it's not hazardous. Okay, but still, if you get a detector and you count the radiation in your room, it will register, a signal. Here is actually a visual way of how what are the challenges that we do have. Okay, and you see that the green dot line here represents the measurement, and you see that patterns that belong to isotopes, for example, the red one, the green pattern, or the orange one here, you see that once they get together, they come from different sources, and but they are registered in the same detector. You see that although they are distinct, okay, once they register, they aggregate, or they convolved, actually is the right process, and we observe the green dot lines. So the difficulty is that, can you extract from this signal the patterns, especially the weak patterns, that are buried in the signal? Okay, so this is actually one of the real challenges that we do have, and machine learning AI has to solve here. For example, I'll give you an example. Here this is a real measurement spectrum, and you see that there is high variation. There are many peaks here. An expert, a person that knows about nuclear physics, can tell you that There are some peaks here. Okay, you can see them. For example, this one. You see, these are two isotopic peaks. Okay, and you have to know actually quantum physics and nuclear physics to understand that these are peaks that these are the possible peaks that come from isotopes of interest. Okay, and the rest one is just background. However, the problem is that, are you certain about that this indeed is a peak in this one? And how certain you are that this is not just because actually radiation here is modeled like random variables, and how certain you are that this is not just variation because of the inherent randomness of the peaks of the radiation. Okay, so the thing is that what actually those features that we need to extract, we need to identify, sometimes they are not very distinct even for the human eye, the expert's human eye. So what we need to do is that we need to resort to, let's say, automated methods and solutions that AI provides. Okay, so why we may use AI in nuclear security? Okay, actually, in this slide, I just summarize all the detection barriers that we do have. Okay, for example, signal to noise ratio. Okay, as I said, we need to extract patterns from the measurement. Okay, the measurements do contain actually the background radiation, which is actually in nuclear is what we call our noise, the noise environment. Okay, in addition to the background radiation, there is also the electronic noise. Okay, because you see that a detector is actually an assembly of electronics. Okay, so there is electronic noise. Also, in nuclear security, when you have a mobile detector, okay, the background radiation, as I said earlier, you change locations of measurement, so the background doesn't remain the same, changes, varies. Okay. Also, another problem we do have in that we need to solve in data analysis is that what about the non-ideal detector response? Okay, what does that mean? It means that sometimes when the detector grows, time passes, the detector, doesn't provide you the most accurate signal. Okay, because of the degradation of detector instruments, because of after a lot of time of using it, it becomes warm, it gets heated up. So the response, the signal actually you get is not as highly as accurate. Okay, detector resolution. Okay, because the not all detectors are of high resolution. That means they cannot resolve, they cannot provide, they cannot measure features of the signals, in the resolution that we would like to. Okay, especially mobile detectors are of low resolution, but we need to use them because they are portable, they are cheap to use. On the contrary, if we use a detector that is of high resolution, these are mostly of them are germanium detectors, and they are they are very high, of highly cost to use them, and they take a lot of space, so it's not really convenient to go with a large detector and survey an area, so they cannot be mobile, in other words. Then we may have signature spectra overlapping. That means pattern of isotopes. Some isotopes might have patterns that they overlap. So once those type of sources, they get together, they provide an aggregation that it's really difficult to extract because of the overlapping. And the last barrier is the spectrum deformation. Means that because, for example, of a shielding, that if you are a terrorist and you want to, let's say, perform an attack, conduct an attack, and you don't want to be detected, that means you're going to have to hide your nuclear material behind, let's say, lead. Okay, so what is actually the purpose of the lead is actually to absorb the radiation. That means in terms of data analytics, is you need to change the signal. Okay, intentionally you change the signal that the detector will see. Okay, and sometimes this signal might totally hide the pattern, or sometimes it might hide part of this pattern. So indeed you need algorithms that can identify what's if something is partially observed there, okay, and correlate it with terroristic activities. Now the practical question we do have, and actually this is where actually AI comes to give us solutions and an answer, is that if you don't have information, if you don't have an expertise on nuclear, okay, you don't know quantum physics, you don't know nuclear physics, uh, can a non-expert, can a person without this type of information, can he or she analyze the data and make accurate inferences? Because all people that work in nuclear security, or you give them a detector and you tell them, okay, go survey an area, they cannot all of them know nuclear physics or be expert to by just observing, using with their eyes, these spectral features that are related with nuclear material. So and the second question we do have here is that even an expert, can an expert observe and identify all details in a data set? So the answer is no. So that's why we need artificial intelligence to provide solution. Okay. So the solution that AI provides is that intelligent data analysis. Okay. It can support decision making about whether there is a terroristic activity, okay, in an urban area. It can reason why it came up with this inference, okay, and support the decision of the operator that might be an expert or might not be. And now with this explosion in technologies, actually with the advancements in hardware, in analytics technologies, we have the big data. Okay, we have actually sensor networks. We can have radiation sensor networks everywhere. We can have hundreds of sensors, radiation sensors, getting measurements, and those measurements, they can comprise data sets that we need to analyze. And in that case, if you have, for example, 100 radiation detectors that they obtain, for example, 1,000 data points per second, I mean, after an hour, you have about 3,000 data points to analyze. No, actually, after an hour. So if you monitor this data, if you utilize the radiation detectors for a whole day, you have millions actually of data points to analyze. So we have a big data. So even if you are an expert, you cannot see every 1 second a new measurement. Okay, you need to have a system do it for you. Okay, so why is artificial intelligence very important in nuclear security? Okay, first of all, it doesn't get panicked. Okay, if it detects a nuclear bomb, it's not gonna get panicked. Okay, so it cannot spread this panic. Okay, second, it can be fast, accurate, precise depending on the algorithm. It can see things, small features in the signal. As I showed to you earlier, the signals that we deal in nuclear security, so it can see more than meets the eye. It doesn't get tired. Okay, it doesn't get emotional. Okay, and it can provide, let's say, a simple interface from detector to human. Okay, in other words, it can analyze the signal and provide in a friendly way the inferences to the operator. And the operator might not be an expert, okay, and can he just read the inferences and make up his decision later. Now, where can we use AI for nuclear security applications? Cargo scanning at ports, okay, baggage scanning at airports, okay, especially for in urban areas, we have AI for threat identification. Okay, you get a detector, you go around and you try to find hidden nuclear weapons. We use AI to continuously monitor radioactive isotopes in nuclear power plants, radioactive isotopes in natural environments, so we can account for those radioactive isotopes. Also, to monitor radioactive material movement in a facility, okay? And something that, is very important for national security, remote sensing, okay? So if an event happens in, let's say, North Korea, you need algorithms that they can, just from a couple of images, they can, identify that indeed there was an explosion there was actually a test of a bomb, okay, that might be of threat, okay. So, and you see, here I have some pictures. We're gonna, for example, here on the top right of the slide, you see that this is a remote sensing image from a satellite, okay. And you see that, those red 2 points here show that there is an indication of an event that has happened. So you need algorithms that you cannot see those with AI. You need actually algorithms that they analyze and identify that indeed there is something there. One of the applications of AI, okay, that can be used in urban areas for nuclear security is that, and has already been done, is in New York, for example, in New York police. Here is the image of a New York police officer that he carries a radiation detector with him, and he gets measurements in the downtown area. Okay, so you see that if someone, let's say, has a potential, he or she is a potential threat to perform attack, in downtown. If he or she passes by the detector will pick up the signature of the nuclear material and will inform the policeman that, okay, this guy is dangerous. Okay. The nice thing actually with AI is that the policeman doesn't need to be an expert in nuclear physics or quantum physics to understand what's happening. Okay. Let's assume the case that, this policeman doesn't have an intelligence system there. His decision is going to be difficult because he's not an expert in that. He might get tired after, some time. Okay. And above all, when you're in a downtown area, you might intentionally or, accidentally get distracted. Okay. If you have a system that always analyzes your data like an AI system, these things are not, a matter anymore to you. Okay. For example, think that, as I say here in this slide, detection decision with AI makes the police officer life work actually easier. Why? Because he doesn't need to be an expert and he needs just a minimum attention. Okay. Once the system picks up something, it's going to warn him. Now, the research solution that we have developed here at UTC for nuclear security is that how we can develop the smart, what we call smart sensors, okay, and then in a more extensive form, smart sensor networks. As I said, the artificial intelligence is part of has extended actually the overall detection system, okay, in the form of software that is being now, let's say, it's being set up actually in the computer that performs the signal analysis and decision making. One of the methods that we have developed here is that what we call the fuzzy logic isotope detection in gamma ray spectra. So this actually algorithm, we're going to see some details later. The goal is to be able to identify features in the form of spectral peaks that belong to special nuclear materials, okay, and match them to our database, to the database of materials that are of interest to that are potential terrorist that they can be potentially used for terroristic attacks, or they can be classified as materials that can be used for other uses. Okay, and the second method that we have developed is that the radiation background estimation using kernel-based Gaussian processes. Okay, And actually, this is a method that we developed it. So if we can estimate background radiation, that means if we can estimate its pattern, then we can extract it from the measurement, and then we can get a clean, hopefully we can get a clean measurement that identification of those spectral features that belong to especially nuclear material becomes easier. Okay, so a few things about fuzzy logic. It's that the fuzzy logic theory says that instead of having the crisp set theory where every object belongs to a set or not, fuzzy logic says that an object belongs to a set with some degree of membership. Okay, and this degree of membership analytically is being expressed as a number between 0 and 1. Okay, and this actually, as the example I do have here, is that you have the temperature, and one value of this temperature might be identified as cold, with belongs actually to the set fuzzy set cold with high with some degree, and at the same time belongs to fuzzy set warm with a lower degree. Okay, so you see that we have a logic here of one object doesn't belong strictly to one set, but belongs to multiple ones. And this one allows us to build, some fuzzy rules that they associate, let's say, inputs to outputs. Okay, they associate something fuzzy to something to another fuzzy thing. Now, specifically for the nuclear security area, what we have done, and the idea was we have developed here was the following. What we used is that we used information from quantum and nuclear physics. Okay, actually, the energy, let's say, the energy of the gamma ray energies of the isotopes. Okay, when they degrade, what are the quanta that they emit? Okay, what type of energy? And what we did is that around those known energies, actually those energies, we develop them, we express them in the form of fuzzy sets. So you see here in the example, we have the isotope neptunium-237, which actually emits a quantum that has energy 0.087 MeV, mega electron volt. So what we did is that we represent this actually as a fuzzy number. The same thing we do, for example, with gadolinium-67, cobalt-60 emits, for example, 2 quanta. So so once you measure cobalt-6, you're going to see that it has 2 peaks at 1.17 and 1.33 MeV. Okay, and if you do all this for all the 700 nuclides that are in the nature, okay, you get we got a fully fuzzy, let's say, database of isotopes. Okay, in this form. So you see that here in the example that this is the cobalt, this is a measurement of cobalt, and you see that this is the real measurement and this is the fuzzy representation. Okay, so our goal is that can we actually match those fuzzy peaks to the real ones, to the measured ones. And once we match this, then what we did is that we developed a set of fuzzy rules that they match every peak to an isotope. Okay, for example, cobalt has 2 peaks, so you expect that you're going to develop 2 rules that they say that if its first peak gets detected, then its detection is true with that degree. Okay, so the output set true is also fuzzy. So we do kind of like, let's say, the benefit of fuzzy logic here is that it allows us to fuse the different peaks into one isotope. Okay, and at the same time incorporate the uncertainty of the signal, because when you're going to measure the signal, you see that the peaks here, because of the background or the inherent fluctuation of these nuclear processes, the peak might be a little bit shifted. Okay, because of the noise, or sometimes because of the instruments. Recall the detection hurdles, that barriers that I told you earlier. But however, with the use of fuzzy logic, we can say that, okay, detection of peak was occurred, but with some degree, if not 100%, then with 90%. So this allows us to model this uncertainty detection. Okay, and at the end, we get all the uncertainties for every peak detected, and we form, the overall isotope detection. Okay, and one of the benefits of this method is that it scans all 700 nuclides very fast. Okay, so it can provide a real-time, actually, data analysis and the identification of radioactive isotopes, and this can allows us to have this software as to be actually to accompany a mobile detector, so to be portable. Okay, and at the same time computationally is not very is not expensive. Now, the second method that we have developed, and this is actually the background radiation estimation, actually here the real challenge we do have here is that we needed to predict something that is totally random. Okay, background radiation estimation is a big challenge in nuclear security. Okay, it's modeling. It's a big challenge now. Nobody actually has solved this problem. The last years, most people try to use machine learning or data-driven methods to analyze and provide models for background radiation, because we're talking about modeling naturally occurring radioactive materials. Okay, and those naturally occurring radioactive materials, they come from primordial isotopes in the soil. Okay, cosmic rays. Okay, and sometimes most of the time they come from urban buildings as well. Okay, so radiation you get when you are in a room is different, for example, in radiation you get when you're in a parking lot. Okay, so when you have a mobile detector that moves from one place to another, this changes because of the background. They cannot be predicted, they cannot be fully estimated, they cannot be modeled. So what we did here is that we developed a smart method that actually what it does is that it gets a real measurement. Okay, decomposes this measurement, the gamma ray measurement, into two type of sets, the non-minima set and the minima set, because the idea was the following: that if a signal, if let's say a beam in the energy spectrum, in the histogram, as I said earlier, has only background, okay, it's gonna definitely be part of the minima set. It's gonna be minimum. We're gonna observe it as a minimum in our signal. Okay, if it has background plus nuclear material of interest, then it's gonna be definitely it's gonna be part of the non-minima set. Okay, based on this, idea, what we did is that we decomposed the spectrum. We ignored the non-minima set. We used the minima set to train our Gaussian process, and then based on the trained Gaussian process, we predicted the number of counts. Okay, actually the values for the ignored non-minima set. Okay, and then we reconstructed our signal by superimposing the minima set with the estimated numbers. Okay, and we get the background spectrum. Now, if the background spectrum coincides to a high degree with an initial spectrum, we say that there is no threat. Okay, if it doesn't, then we say that okay, there is a potential threat in our method. Okay, so you see that for the minimum set, you can see here in the slide that minima is this type of energy channels. Okay, in the second step, you see that what I just described, how the decomposing to training and target data happened. And then the last part was the superimposing of the estimate to the minima set. So actually we reconstructed a new spectrum and a final new spectrum that we call final background, and we compare it to the original measurement to see whether they match or not. Now, based on these AI solutions, where can we find AI, where it's going to be applied? Okay, to fully have an efficient nuclear security architecture, we need smart rad sensors everywhere. Ideas are: can we place radiation detectors in taxis? Because taxis can comprise of a sensor network that adversaries cannot predict. Okay, wherever someone is gonna go is gonna find the taxi. Or the best is that can we develop so small detectors that we can put them in cell phones, because cell phones are everywhere. They can be used as a, let's say, global sensor network. Or recently they have been used radiation sensors in planes, okay, that they fly over urban areas and they can get measurements whether they and identify whether there is a nuclear weapon or material, underneath the plane. However, nuclear security, although it has those benefits, it enhances security, but also it has some, problems. For example, wrong use of the AI methods, in nuclear security, even if the algorithm is not being developed well, or it has a bug in the code, you can have a false alarm or you can have a miss, and a miss in nuclear security means is counting lethal in deaths. Okay, so you cannot have systems that are robust. You have to have systems that they are fully accurate. Okay, also when you monitor radiation, you have privacy issues, because if you have an algorithm that identifies radiation is information, and let's say there is privacy issues in the sense that if someone goes under radiation treatment and it passes by a radiation detector and you detect that he emits something more than the natural radiation, then this guy, you say, okay, this guy has gone, he has cancer, or he has, he goes under radiation treatment. So there are privacy issues in using AI, with for nuclear security. So when we develop those systems, when we develop AI for the area of nuclear in general, and nuclear security even more, the AI systems should be very well tested. Okay, we prefer having false alarm than misses, so we need to minimize the risk of having misses, because as I said, a miss is counted in deaths. A false alarm is okay, it just costs, in dollars. Okay, a problem that we have so far is that even if cybersecurity solutions are the best, nuclear detectors and nuclear systems are not fully connected to the internet. Okay, because the best security is not to connect something to the internet. Okay, let's assume that we have a sensor network like in taxis, and then these detectors on taxis, they need wireless links, to to transmit actually their data, so they are vulnerable to cyber attacks. Okay, also they might be the nuclear security technologies are high cost technologies, especially if you need detectors of high resolution. The costs, go very up. So we need to develop methods that they are cost effective. Okay, something that, it has impact on social life is that false detection of radioactive source. Imagine that you have an AI system that falsely says that, okay, this guy has a radioactive source on him, on her, or her, and he's a potential terrorist. Okay, you cannot wrongly accuse him. He's gonna file a lawsuit against you. Okay, so you really have to be certain that, the algorithms work in a perfect way. We cannot have algorithms that, provide false detection in ports. Okay, because if they say that, okay, open this cargo, there is something there, this also has a high cost. Okay, and this also might, provide high delays in, having the products, passing by the border. Okay, detecting actually utilizing actually these technologies for checking everything that comes into the border, or having radiation sensors in all big cities, is high cost for governments. Okay, so you see that these are things that they have we have concerns about them. Okay, and how we can deal with them, especially the wrong accusation is something that, we really need to be discreet how and where we're going to use the detectors. As I said, privacy reasons. As I said earlier, that, with the radiation sensor network, they're like cameras. Okay, they reduce the privacy. Okay, so you can identify activities, or especially with health issues, about if you use radiation sensors. As I said, the example of radiation treatment. Okay, now about the future. AI definitely can help make our rad sensors even smarter. Okay, it can allow to have sensors that are autonomous. Okay, that they take their data, they process, they make the decision, they transmit. Okay, in general, they enhance the security and safety, okay, by just monitoring the urban areas, okay, but also at the same time they provide new ways for cyber attacks. Okay, we have to be very careful about how and where we're gonna use them. So to summarize, okay, just presented today how AI is used in nuclear security, national security, in actually mainly in energy security. Okay, some solutions that I have developed while I was at Purdue, and still continue here at UTSA. For example, the fuzzy logic for source identification, the Gaussian processes. At the end, I talked about the responsibilities and social impact of AI and how and issues that we have to deal with. And thanks for your attention. Okay, this is actually the work that we continue here is part of the consortium for on nuclear security technology, which is funded by DOE and includes UTSA, St. Mary's University, and University of Nevada at Las Vegas. So if you have questions, comments, or suggestions, you are welcome to throw them to me right now. Thank you so much. And sorry for taking all 8 minutes more than the allocated time.
No, this is perfect, Miltos. Thank you so much for sharing. I think the students needed to hear how AI is being applied in a completely different context, which they're probably not familiar with.
Mm-hmm.
This is phenomenal. Thank you so much for sharing. So the floor is open for questions. I'm just trying to see, you either can raise your hand or type your question in the chat. Okay.
Hi. Can I ask
Gabriella.
you a question? So what are the next steps? What is the next direction that you want to take? Given all the different constraints on security, what do you think, where do you think the stronger guarantees can come from?
Okay, so by constraints, I guess you mean the technical constraints or
Both
the
technical or
society?
context, both of them.
That's a really good question. The thing is that we need to go, first of all, technically, because actually the main direction is that if we can manage to develop algorithms that they don't miss, they have very low false detection, and actually you guys are, all of you, I'm pretty sure you have heard the word explainability. Okay, so one way is that to be able to develop those algorithms, and used and being trusted by everyone, you have to have algorithms that they explain what they do. Okay, that so if you have and I think that's the direction that both technically and from a society point of view, if you have an algorithm that detects something and explains why it detected, that's the direction I would like to follow. Okay, and that's gonna make the algorithm more trustworthy. Okay.
Thank you. Yeah. Thanks a lot.
Ashkan, did you had a question? I saw your hand raise and
Yeah, that actually was my question. But if I could just ask one other thing, could you remind me what signals we were looking for specifically?
Actually, there are many types of signals, but me personally, I work with gamma radiation. The thing is that in nuclear security, we have two magic words. One, we call them signatures. Okay, means that a priori information we have about a nuclear material, and there is also the second magic word that's called observables. Okay, and observables is about let's say a fusion of signals that indicate the existence or presence of nuclear material. For example, I'll tell you one thing. Except for taxis, cell phones, do you know what else can be used as a sensor network that is almost everywhere in urban areas? Do you have any idea?
Uh, other than physical cars, I can't think of much else.
Cars. Cars, yeah, indeed, and taxis are, a network. I would tell you power system. Power lines are everywhere. Can you imagine? There is research now that to see that how, for example, when a nuclear material passes by a power line, how the electromagnetics change, and this variation in electromagnetics can it be observed? This is an observable, okay? And if you see this change can then ask for example, a policeman to tell him, okay, go and check this guy. We have an indication that there is something let's say risky with him. Okay, can you go next to him and check him with a radiation detector to get a second source of information and fuse the data. Okay, so you see that typically nuclear security uses radiation data, but the new directions say that, okay, we can fuse any type of information we need. Okay,
it's a very interesting concept. By chance, do you know how, I guess, false positive proof that would be from other signals and that are going on in the city life?
Yeah, the problem with false positive is that I'll tell you. Let me the signals here. Let me show you. The signals here, they have a high variation, okay, and the problem is that they give a lot of false positives. That's one of the challenges that we have here. We do have right now, and DOE tries to solve the high number of false positives. So far, the research has failed actually to reduce, the number of false positives. Okay, was that your question?
Yeah, that was. But my question was, I guess, more of a, I guess, a theory question in this application with power lines. Just if you had any knowledge on.
I will tell you that they have reduced the false. But by fusing data, they have reduced the false positives. I can tell you that. But this is also research that is being done in national labs and is very classified. I will tell you the following thing, that when the IAEA agents went to Iran to check whether there is a reprocessing facility to make the spent nuclear fuel material to bombs, the Iranians, they could hide radiation by shielding all the material, but what they could not hide was the energy consumption they used, because those devices, for example, the centrifuge device they used to change the material, make it weapon, consumes a lot of energy. So the AI inspectors, although the radiation detector showed nothing, once they checked the energy consumption, they realized that, okay, there is a problem here. Okay, so you see that this is another example of how the power lines, let's say, power consumption was used to the power pattern was used, to identify an illegal activity.
Okay. We have a few more questions. Anurag?
Hello. It was a great talk, Dr. Alamaniotis. Thanks for that. Falling back to a question about false positives and false negatives, right? So based on this application, the more critical aspect, as you have mentioned, is false negative, right? If we get a false negative, that is
the miss, what we call a miss, because as I said, Anurag, a miss, you count it, it leads to deaths. Okay, you cannot miss a bomb. It's better to accuse someone. I mean, if you have a false positive, it's gonna lead to loss of money. You're gonna lose money. Okay, but if you miss, you're gonna lose lives, and you don't want that.
Yeah. So one question that I had was like, how do we ensure that the model does not give false negatives? Like one way, like if I think of it in a other like neural networks perspective, I can think of it as like maybe trying to overfit the model, which would significantly reduce. But are there any other concepts or methods which are used to make sure that you don't get these false negatives? Maybe it's the data distribution itself, which is
Okay.
usually like make
Yeah,
sure.
yeah. Yeah, that's a good technical question. I can tell you that no, there is no method to ensure that you don't get any false, you don't get any misses. Okay, there is no. The only way is to even when you have a small, let's say you have an algorithm that provides you says that there is an anomaly detection, a threat with small certainty. You have to even that you have to take into consideration. Okay, so there is no method from a data analysis point of view. No, there's no method.
Yeah, in a way, we have to set the threshold very low, probably.
Right.
For
Yeah.
anomaly.
Very low. Very low. Yeah. Very low.
Okay.
And that's the problem. And that's why DOE spends a lot of money now try to develop detectors, because the nuclear security has a research, not only data analytics, but also for many years now there is a huge research in materials. How can you detect? How can you develop materials that it can be used for providing high resolution signals? Okay, because actually radiation detection is actually is based on electrical engineering. Okay, you need the particles that enter the detector to induce a voltage difference. Okay,
Yes.
so if you have a material that induces voltage difference, very easily, then you get, a lot of false positives. Okay, that's a difficult now. So there is it's very complex type of research. It incorporates a lot of things. Okay, I work in data analytics and AI.
Yeah, thanks a lot.
You're welcome.
There's one more question in the chat from Peng Wei Shao. Training AI requires a lot of data. How do you collect your data?
Okay, good question. With radiation detectors, okay, here at UTC I do have one, and you might see some of my students going around campus and getting background measurements. Okay, but also personally I collaborate with the national labs. Okay, Argo National Lab has provided me with a lot of data. Los Alamos has also given me real world data, and for some isotopes that some data sets are classified, we cannot get them, we have to simulate them. Okay, there are simulators like particle-based simulators. I'll tell you one that is open, is called Giant 4 from CERN. Okay, but you need to know very good C++ to set up the simulation of what detector you are going to use, what source you are going to try to detect. Okay, so for let's say for plutonium, uranium, isotopes, we do simulations. And personally, I have this, and this is an experience that I'm very glad that I had to. I have got data. I went to Nevada National Security Site 7 years ago when I was at Purdue, and we got measurements of gamma ray measurements from nuclear weapons. Okay, Nevada National Measurement is actually next to in the desert of Nevada, next to Area 51. Okay, so all these military areas are there. So I had the chance to go there and get some real measurements that I still use them. Okay, these were unclassified measurements, so I could use them.
Okay. Thank you so much, Miltos. I don't see any more questions.
Okay.
Oh,
No,
actually, there's one more question, I
okay.
guess. From Praveen, it's continuing on Anurag's question. If we don't have mathematical guarantee with AI models, how are we able to trust these systems? I think this points to some of the things you discussed at the end, Miltos.
Okay. Well, we don't fully trust them. That's why we get money from DOE, okay, to develop them. No, we don't fully trust them now. No, so far, no. No. But I guess, as we said with Anurag earlier, if you set up the threshold, the detection threshold very low, what you do is that you prefer having a lot of false alarms than miss something. Okay, so that's the strategy so far. That's okay. Let's pay a little bit more. Or the only thing that I would say that it actually it happens. It's not, you know, I'm not very proud to hear that, but anyway, is that, for example, in New York, when you have so many cargos coming, you know, overseas, you cannot check all of them. So what they do is that they sample which cargos they're gonna scan for nuclear threats. Okay, so this is the only case I would say that the detection they do there, the survey they do there is trusted, but it's not very. The whole process, you cannot trust the whole process because they scan only 1 per 10 cargos. Okay, so unfortunately, there is not the ideal way here, at least up to this point.
Okay. A lot of work to be done in building explainable AI systems and ensuring that these are interpretable and have credit assignment and
Bravos.
yeah.
Especially for privacy issues, because privacy is very important here. Okay, you cannot accuse someone that passes by you, because if you have a false alarm and someone passes by you and your detector says, okay, he's potential terrorist, if you accuse him, you're done. Okay, he can, you know, file a lawsuit against you. So we really need to be careful in that.
Right. Okay, and there are researchers in Matrix, including Miltos and several others, who are working on building such trustworthy systems. So hopefully we'll have more conversations on these topics. Thank you all for joining us today. And this talk will be posted on YouTube. And if you have further questions to Miltos, feel free to reach out to him. Thank you so much.
Okay, thank you for hosting me today. Thank you, Derisa.
Yeah, bye.